Okay, so we're going to work through the solutions for the Assessment 5 review here. So in the first problem, it says it is estimated that the school CO2 levels average at 1,200 parts per million. So in number one, that is a statement about the population parameter. So we're going to assume that the mean averages around 1,200 with a standard deviation. So there's the population standard deviation at 300. And it says we're taking a random sample. So the random sample is size 30. What is the probability? So it's the probability that the CO2 level is more than 1,000. Okay, so we want to know that the mean of the sample is greater than 1,000. Okay. All right, so let's think about this a little bit. If we're talking about the mean of the sample, the means of the samples are distributed normally here, right? And we're good with it being normal because the sample size is over 30, and the population is, well, the sample size over 30 gets to be normal. We can then know that because the mean of the samples are distributed, this is going to have an unbiased indicator, so this is going to be right at 1,200. And then also because the sample size 30 is definitely less than 10% of the number of possible days. I mean, there's like, hundreds and thousands of days that we could be sampling. Or it's number of schools, right? There we go. There it is. The number of schools. Schools is the thing. So yeah, 30 is definitely less than 10% of all schools. So sigma here is going to be the sigma 300 over the square root of the sample size 30. Okay, so let's think this through. My z-score, right, is going to come from the fact that we're normally distributed, right? So z-score should be x bar minus the mean of the x bars over the standard deviation of the x bars, okay? So I want to calculate this, and one of these is going to be equal to that. So I'm going to build out. So if I think about this, P of x bar is greater than 1,000, right? So this should be the same as x bar minus the mean of the x bar should be greater than 1,000 minus the mean of the x bars. So it's just subtracting both sides of the inequality. This should be the same as that over sigma of the x bars is greater than 1,000 minus the mean of the x bars over the sigma of the x bars, right? So kind of using my knowledge from the problem here, this, my z-score formula, is going to say that z has to be greater than 1,000, but I know that the mean of the x bars up here is 1,200. So that's 1,200. And the sigma of the x bars is right there, which is 300 over the square root of 30, right? Over the square root, sorry, that's not helpful. Let's bring that over to the side again. There we go. 300 over the square root of 30, right? So, and I got that from right here. There's sigma of x bars, 300 over the square root of 30. So the probability that x bar is greater than 1,000 is the same that the probability of its z-score is greater than 1,000 minus 1,200 over 300 over the square root of 30, which looks like answer A. Okay, so there's number one, answer A. All right, so there you go. Let's look at number 2 here. Problem number 2 says a study is to be performed to estimate the proportion of voters who believe that the economy is heading in the right direction. Which of the following pairs of sample size and the proportion P will result in the smallest variance? Okay, so remember, variance is the standard deviation squared. So that's going to be P times Q over P times Q. P times Q over N squared, which is just P times Q over N, right? So problem A is 0.1 times 0.9 over 100, which if I go and grab my calculator, that is, turn that on, 0.1 times 0.9 times 0.9 divide by 100 gives me, let's see, that's going to be 0.0009. Part B would be 0.5 times 0.5 over 100, right? Because if P is 0.5, Q has to be 0.5, so 0.5 times 0.5 divide by 100 gives me 0.0025. Part C says 0.99 times 0.01, right? Over 100. So let's try that one. And that one comes out as 9 so that's like 0.000099, right? And then part D would be 0.1 times 0.9 over 1,000, right? So I'm going to get 0.1 times 0.9 divide by 1,000, zeros not nines, right? Gives me 0.00009 times 10 to the 5th, right? So looking at my possibilities here, it asks me for the smallest variance, which this one is just a wee bit smaller than that one. So we're going to go with D. D is my answer there. All right, so let's look at number 3. Suppose a population is skewed right. Which of the following sample sizes would the sampling distribution of x bar be closest to normal? Okay, so central limit theorem not only says that we have to have n greater than 30, but it also says that as n gets closer, the distribution of the mean of the x bars gets closer to normal. So what we want to do is we want to pick the largest sample size here, which would be C at 100. Okay, so there we go. D is definitely false because A is not going to work, right? So we cannot assume normalcy at all from A, but law of large numbers says that as we get higher and higher, this is going to get closer and closer to normal. All right, so let's look at number 4. Which of these is a true statement? Okay, the sampling distribution of P hat has a mean equal to the population proportion of P. That is definitely true because we like to say that this distribution is non-biased. So we would expect that the mean of P hat should be equal to P. That's our answer. let's look at the why the other ones are wrong. The standard deviation for p hat should be equal to p times 1 minus p, which we're calling q over n, which is not the same as the answer there, so that's not correct. C, the sampling distribution for p has a standard deviation that becomes larger as the sample size becomes larger. Well, again, because this is p times q over n, as n's getting bigger, this is getting smaller, which is the exact opposite of what C says. And D, the sampling distribution of, that shouldn't be a semicolon there. Let's fix that. Of, lots of extra letters there, of p hat is considered to be close to normal, provided that n is greater than 0. That would be true if you were dealing with x bar, right? But the central limit theorem only applies to x bar, not to p hat. So that's where D goes awry. Correct answer here is A. All right, so let's look at number 5. In a school of 2,500 students, the students in AP Stats class are planning a random survey of 100. So population size is 2,500, sample size is 100, and we want to know the proportion who would rather drop lacrosse than band. All right, so the teacher says move your sample size from 100 to 200. Okay, so we're still within the range of the 10% rule here, so that's good. And if you think about the standard deviation of p hat is pq over n, and as n is going from 100 to 200, this is getting smaller. And standard deviation is a measure of variability, so this would be reducing variability. Answer there is B. So there you go. Let's look at number 6. 6 says the distribution of ages of people who died last year in the United States is skewed left. What happens to the sampling distribution of means as the sample size goes from n equals 50 to n equals 200? Okay, so you would expect here for standard deviation, which is sigma over square root of n, to get smaller because n is in the denominator, right? And we would expect, as n is getting larger, we would expect to be moving closer to normal because of CLT, the central limit theorem. So the mean is always unbiased, so the mean is going to stay the same, the standard deviation becomes smaller, and the shape becomes closer to normal by the central limit theorem. D is the answer we're looking for there. All right, let's look at 7. Which of the following are unbiased indicators? Okay, so the sample mean is an unbiased indicator, right? We know that. Sample mean, so the mean of the sample means is equal to the mean of the population. Sample proportion, the mean of the sample proportions is equal to that. All right, so let's think about this. If the mean is unbiased, then the mean of, let's say you have 2 different sample means, right? So the difference of the sample means of x bar 1 minus x bar 2 should equal mean minus mean, which should be going to 0, right? So, I'm not thinking that through. It should be mean 1 minus mean 2. If this is an unbiased, it's basically saying, look, let's kind of think this through backwards here. Being a little bit facile here. The 0 doesn't work there. Mean x bar 1 minus mean x bar 2 should be equal to mean minus mean, which means that the mean minus the mean is equal to the mean minus mean. We get unbiased from that. Similarly, mean p hat 1 minus mean p hat 2 should just be p1 minus p2. So a difference of sample proportion should also be unbiased. They're giving you the same thing. So in fact, all of these are unbiased indicators. Nothing untoward here. Variability is what's in play here, not bias. So we'll get into that a little bit later on. All right, so let's see, that's 7. Let's look at 8. 8 is very similar to number 1, except for we're doing it with a proportion here. So we're given that the assumption is that 12% of the butterfly larvae are experiencing mutation. So P is 0.12. We want to know the probability that a sample of size 300 would be more than 0.15. So remember, Z here is going to be P hat minus the mean of the P hats, right, over the standard deviation of the P hats. So building this out again, you can play the same game we did before. Oops, I forgot if I subtract the mean of the P hats from both sides, and then divide both sides by, there we go, 13 times 8. The standard deviation of the P hats, right? Standard deviation, I'm going too fast. The P hats means that this is the same as this, is the same as this, is the same as Z is greater than 0.15 minus the mean of the P hats over the standard deviation of the P hats. Now, by because this is a what's it called, sampling distribution, we know that the mean of the P hats has to be equal to P, which is 0.12. The standard deviation of the P hats is going to be the square root of 0.12 times Q, which would be 0.88 over the sample size, which is 300. So this would be rewritten as 0.15 minus 0.12 over square root 0.12 times 0.88 over 300, which looks a lot like that looks a lot like B, right? That one's B. Okay, so there we go in that problem. That's number 8. Let's look at number 9. We're going to have football players here, right? Football players and concussions. Great. Number 9 here says we're assuming that the average number of hits to the helmet are 355 with a standard deviation of 80. So we're going to grab 48 players. We're going to take a sample of 48 out of all football players, which is like way less than 10%. But it's over 30, so we meet the central limit theorem. This means mean of X bar should be 355. Standard deviation of X bar should be, what is that? That's 80 over square root of 48. Well, let's get a number for that. Seems to be giving about 11.547, right? So I want to know the probability that 340 is less than or equal to x bar is less than or equal to 360. All right, so let's grab that. That's normal CDF. The lower bound is 340. The upper bound is 360. The mean in this situation is 355 with a standard deviation of 11.547. So let's grab an answer. And that comes up as 0.5705, which looks like C. Okay, so not so bad on number 9 there. 10, I have to admit there is something in this that is not in this portion of the course yet. So I will walk through it. It will not be a question like this on the assessment. So you have two populations here. You have sleep trained babies that have a mean of 1.2 and a standard deviation of 0.3, and you have non-sleep trained babies that have a mean of 1.8 with a standard deviation of 0.5. So what I've done is I've pulled 40 from each of these, right? Because half of my sample is coming from each of these. So here's the problem. If I take mean 2 minus mean 1, that value should be 0.6. So this is going to give me mean 2 minus mean 1. The mean of the difference is 0.6. Here, standard deviation is a little weird, and the way we're going to calculate that is we're going to hold on to this for a second, okay? But we have to use these to do it. So right now we know we have an unbiased indicator. So the mean of the samples of the differences should be the mean of the differences, which is still 0.6. And that's going to work because the two it's just like grabbing any two together. It's unbiased, right? So this is like, I don't know how to put this. The mean of x bar 1 minus the mean of x bar 2, right? The mean of the two differences is going to be m1 minus m2, mu1 minus mu2. Sorry, 2 minus 1, because these guys are sleeping or waking up more often. So it's going to be 1.8 minus 1.2, which is 0.6. Okay. So this is what I want here. The problem is that if I want to get variability here for sigma of x2 minus x1, I have to go back to variance, right? So variance of this is 0.3 squared, and the variance of the other one is 0.5 squared, right? So that's going to be my new variance. And because I'm taking like half from each, I only have 40 samples here, right? Because I have 40 of one, 40 of the other, and then I'm subtracting them, right? So this is going to give me my new variance. And when I take the square root of that, that's going to give me the the standard deviation of the population. So again, don't spend too much time on this. We're going to do a much deeper dive on this later in the course. But this is how this number is coming to be. So we're going to get a squared there. No, sorry. Remember, when we're doing difference of standard deviations, you add the variances. So that's going to be a plus, actually. Plus 0.5 squared, right? Then I'm going to divide that by the 40 different pairs, and then take the square root of that to get me back to standard deviation, which is going to make this 0.0922. All right, so kind of playing this out, I'm going to say mean of my x bars is going to be 0.6. The standard deviation of my x bars is going to be 0.0922. And I want to know the probability that x bar is actually more than 0.75, right? So we use second vars normal CDF. My lower bound is 0.75. My mean is 0.6. My standard deviation is 0.0922. And upper bound is an extremely large number. There we go. Mean is 0.6. There we go. Standard deviation is 0.0922. That's all the blanks. And this is going to say that that probability is a little bit more than 5%. Now, like I said, don't 0.59, I think that is when I round it, which is answer A. Don't spend a whole lot of time on this problem 10. It's not going to show up on your assessment, and we will do a much bigger dive into pooled and non-pooled samples a little bit later in the course. So hang tight with that one. All right, let's look at the free response stuff here. The free response here are somewhat theoretical questions. Part A, so you've got 3 parameters here. Well, one is actually 2 statistics and a parameter. Your sample size is 90. The mean of your sample is 6.5. The median of the sample is 3.8. So I guess they're all statistics. Okay. So given this information, what do we think about the distribution, about its shape, right? This is probably skewed right. And the reason why we think this is that the mean is significantly larger than the median. When the mean is above the median, that indicates skew right of some sort. Okay, so this data is probably skewed to the right. B, are the conditions of inference met? Okay, so the conditions of inference would be, is the sample less than 10% of the population? And given that the sample here is 90, and the population is the number of men that work on Wall Street, I'm pretty certain that that number is going to be bigger than 900. So we've got that one. The 10% rule is going to be met. And the second thing that I need to have is that n has to be greater than 30, and 90 is definitely greater than 30. So we're good for conditions of inference, right? So this is the 10% rule. That gets me the correct standard deviation, and n being greater than 30 is going to say that I'm normal enough to draw an inference, right? Part C is that if I took a bigger or a different sample size, right, and it resulted in Cx bar increasing, then would the sample size be bigger or smaller than 90? And I know that Cx bar is sigma over square root of n. So if sigma increases, this would imply that n is decreasing, which means sample size is smaller. Because I'm getting more variability, I should get a smaller sample size. Okay, so there's walking through the problems from the review. If you have questions, feel free to email, reach out. I'll see if I can help out, and we'll go from there. Once you're done with this, move on to the assessment. The assessment's going to be due on the 19th at 8 a.m., and we'll go from there. Good job.